Hello students, welcome to IMS GATE Academy. In the foundation course, I started the subject of electronic devices and circuits. In the last session, I did insulators, conductors and semiconductors. But in the semiconductors, I did only intrinsic semiconductors. In today's session, I am going to discuss about PN junction diode. In the PN junction diode, we need to understand well about p-type and n-type extrinsic semiconductors. Without knowing p-type and n-type extrinsic semiconductor, we cannot enter into PN junction diode. Anyhow, the today's session is PN junction diode. Initially, I will give some information regarding p-type and n-type extrinsic semiconductor. Then after I will start PN junction diode. Understand? Yes. The topic is PN junction diode. PN junction diode. We are saying now. But to know well about PN junction diode, initially we need to know what is p-type extrinsic semiconductor, what is n-type extrinsic semiconductor. Without knowing those two materials, I cannot start PN junction diode. So initially I wish to select extrinsic semiconductor. We should know well about the extrinsic semiconductor initially. Without knowing extrinsic semiconductor, we can't do anything. After knowing extrinsic semiconductor, I will start PN junction diode, I said. What is extrinsic semiconductor? In the last class, I explained what is intrinsic semiconductor. What I explained? A pure type of semiconductor is called as intrinsic semiconductor. When we can say the material is very pure in the semiconductors, whenever concentration of electrons and concentration of holes are equal, I said already, it is an intrinsic semiconductor. But that pure type of semiconductor is not so used in practical application. Good evening, Thirumal Reddy. Pure intrinsic semiconductor we cannot use in practical application. What is the reason behind it? The reason is it doesn't have good conductivity. The required conductivity we cannot find in the intrinsic semiconductor. In that case, it is required extrinsic semiconductor. How extrinsic semiconductor is formed? You must select intrinsic semiconductor. You must select intrinsic semiconductor. That is to be doped with impurity atom. You must doped with impurity. Doped means just added only here. Impurity. Impurity, this is nothing but the doping we can call. Doping of atoms will be done. Then it is available extrinsic semiconductor. Extrinsic semiconductor is available. Sir, what is the doping? Doping indicates the addition of atoms only now, addition of other atoms only now. That means intrinsic semiconductor contains identical semiconducting atoms only now. Intrinsic semiconductors contain same size of atoms only now. But along with these intrinsic semiconductor atoms, when you are adding any foreign atoms there now, any foreign atoms you must add only now. Then only it is going to form the extrinsic semiconductor only now. But addition of that impurity only we are calling as a dopant only here now. Sir, why we are adding the impurities are? Just now I said for the sake of increasing the conductivity of the material only we can say. But how many types of impurities are possible here? There are two types of impurities. Impurities are of two types only, we can say. Impurity is divided as two types only, we can say. One is said to be trivalent atom, trivalent atom. The second one is said to be pentavalent atom, we can say. Pentavalent atom. Pentavalent atom. These two are said to be what now? Impurities only. What is pentavalent atom? Whenever any atom contains 5 valence electrons, we can call it as a what now? Pentavalent atom only. An atom which contains 5 valence electrons is said to be pentavalent atom. Trivalent atom means atom which contains 3 valence electrons is called as a trivalent atoms, we can say now. There is a trivalent atom. It contains 3 valence electrons only, we can say. So, what are the examples we can give? That I will give while doing the what now? When the addition is made pentavalent, what are the examples I will give? When added intrinsic with the trivalent means what we can call, and what are the examples I will give. And one more point you have to understand clearly. Whenever intrinsic semiconductor is doped with any impurity, that means whenever it is added with impurity, at the time structure of the material will not be changed, one doubt is going to arise. It does not have any variation of the structure in the body only. In the intrinsic semiconductor, what structure is existing in the material, the same structure is going to remain in the extrinsic semiconductor only. The reason is what? The impurity addition is made very small they will dope only, we can say. But what amount of impurity is added, I will give shortly now. Anyhow, the addition of impurity is made very small. That is why the structure of the material will not be changing in the extrinsic semiconductor, we can call, say it. Understand my point now. And next ones. But here the extrinsic semiconductors are of two types. What they are, I will give one by one. There are two types of extrinsic semiconductor, we can say. There are two types of extrinsic semiconductor, ESC I am putting, extrinsic semiconductor. There are two types of extrinsic semiconductor. One is said to be N-type extrinsic semiconductor, N-type extrinsic semiconductor, and second one is said to be P-type extrinsic semiconductor. Without knowing N-type and P-type extrinsic semiconductors, we cannot enter into the PN junction diode. Initially, we need to know in this class. Thereafter, I will start how the PN junction diode is formed, how that working principle, how the energy band diagram, and everything you will know shortly. Understand now. But initially, I selected N-type extrinsic semiconductor. N-type extrinsic semiconductor. How this is formed? Suppose I selected initially intrinsic semiconductor. This is mixed with, added with, doped with, anyone it is allowed. Doped with what? Pentavalent atom. Pentavalent atom. Pentavalent atom. Then it is going to form N-type extrinsic semiconductor. Then it is going to form N-type extrinsic semiconductor. The addition is made those two only now. But what are the examples of pentavalent atom? Examples of pentavalent atoms are nothing but examples of pentavalent atom. What we can take? Atoms. Examples of pentavalent atoms are, we can say antimony. Generally, we are going to use antimony. Antimony, arsenic, Like we can take now, and also even you have taken the what now as phosphorus. All this comes under the what now pentavalent atoms only now. Phosphorus or antimony or arsenic, these are all the examples of pentavalent atoms only we can see. Understand my point now? But what is going to happen when it is doped? I will explain now. Suppose I selected here as an example, I selected here now pentavalent atom of antimony I have taken here now. For example, this is antimony. Antimony means they will put SB. SB only. But the configuration of this N-type extrinsic semiconductor I want to draw here now. You will get some idea about the subject. This is nothing but germanium or silicon, anyone you can select. I have taken silicon this side. This is silicon. Why this diagram? You can understand clearly now. Why this diagram? You will know. But this is silicon. Still structure goes this side and this side and this side. The structure will be going this side and continuation possible this side. This is possible this side. This is possible this side. The structure goes like this, possible. But antimony contains how many number of valence electrons? I said 5 valence electrons. 5 valence electrons I can put in this way. There are 5 valence electrons in antimony. How many valence electrons had by silicon? Silicon comes under 4th group. 4th group means it can have 4 valence electrons. It can have 4 valence electrons only now. Here, whenever sharing of any 2 electrons are taken place, thereby forming a covalent bond. Whenever sharing of any 2 electrons are taken place, a bond is formed. That bond we can call it as a covalent bond. Covalent bond is going to form here now. But how many number of the bonds are going to form? This is one more covalent bond due to sharing of these 2 electrons. Due to sharing of these 2 electrons, one more covalent bond. Because of the sharing of these 2 electrons, one more covalent bond. So when an antimony atom is what now added, that is going to have the what now, that is going to form 4 covalent bonds from the surrounding 4 silicon atoms only now. But this electron, one more electron you got here now. Which electron? This electron doesn't have any more electrons to have the sharing only now. When it doesn't have any more electrons to form the bond, it can stand as an excess electron. Excess. This can stand as an excess electron. This is going to remain as an excess electron only now. This is going to stay as an excess electron only now. So this excess electron is a free electron. One more way we can say that excess electron can stand as a free electron only now. That electron will not stay within the bond. It is going to move freely anywhere in the what now semiconducting material. It is going to move freely within the semiconducting material. Due to that temperature, it is going to move only, we can say now. But here, in the energy band diagram, these are the excess electrons will occupy the space at what particular point. Where it can occupy means, suppose energy band diagram you have taken like this. You have taken energy band diagram. You know very well, this is nothing but valence band energy only. This energy we are going to call conduction band energy only. EC we can write. The excess electrons which are so developed due to the addition of the impurity will try to occupy one particular position only now. What position? Just below the conduction band, they are going to occupy the space. These are the excess electrons will occupy this place only, we can say. But excess electron, these are said to be donor atoms also. Donors also we can call. Atoms are donating one excess electron. This antimony donates one excess electron only now. So excess electrons will come and occupy one energy level. That energy level we can call it as a what now? ED, donor energy level we can call. That means this is the energy level is the possible here now, some energy only now. Now the point what I wish to say, but the n-type extrinsic semiconductors, what are the majority carriers we have? If I ask, anybody can say electrons are the majority carriers only now. We may get a doubt, sir, how can you say the n-type semiconductors contains majority carriers of electrons are? Here you watch. Suppose I selected one intrinsic semiconductor initially. I selected intrinsic semiconductor. In the energy band diagram, what happens? You watch it now. This is nothing but the conduction band. This is the conduction band. This is nothing but the valence band. Sorry, this is the valence band. Below one is the valence band. You know. This is valence band. This is nothing but the conduction band. Because of the temperature, what is going to be at room temperature, you can find certain number of electrons to move from valence band to conduction band. When 4 electrons are reaching to the what now conduction band, 4 number of holes are going to generate. How many electrons are moved, that many number of the holes are generating, already we know. This is intrinsic semiconductor. What now? Energy band diagram, you know very well. But here we cannot say electrons are more as compared to holes, not allowed. Holes are more as compared to electrons, I cannot say. Both are equal only now. But the n-type extrinsic semiconductor, what happens? Due to increase of temperature, these electrons are needed very less temperature only to move from the what now? From here to here. This electron will try to move and occupy this space only now. Like that number of electrons are going to move and occupy the space in the conduction band only now due to the temperature now. And also the temperature which is existing in the atmosphere can allow certain number of electrons to move from here to here, it can allow to move. Like that what now? One more hole, one more electron. One more hole here now, one more electrons. Like that number of electrons and number of what now? But like that electrons are forming. Finally, what now? Here you catch my point. The electrons which are existing in this band due to temperature moving to the conduction band. After reaching to the conduction band, they will not allow to create the holes in this energy band diagram. In the energy band diagram, we cannot find any number of the holes only now. Only electrons transfer only possible now. These electrons we got from the excess electrons only now. At the time creation, the holes are not possible. That's why here the number of electrons are more in the conduction band, but the number of electrons in the conduction band are more, but the number of holes in the valence band will be less only possible now. That is why the majority carriers in the n-type extrinsic semiconductor are electrons we say. That's why we can write only one point. Majority carriers. Majority carriers in n-type extrinsic semiconductor are electrons we can say. We can find electrons only now. That information is required. What I explained so far, when intrinsic semiconductor is doped with pentavalent atom, yes, it is going to form n-type extrinsic semiconductor. As an example, I selected antimony. Antimony, if you selected, antimony contains 5 valence electron. The semiconductor, intrinsic semiconductor like silicon is taken that contains 4 valence electrons, due to sharing of electrons, 4 valence covalent bonds are formed and one excess electron is going to remain. One excess electron is going to remain, I said now. The excess electrons which are so produced will occupy the space just below the what now? Conduction band only now. These are the excess electrons can also be called as a donors, I said now. Whenever a temperature is received by the what now? This extrinsic semiconductor, the electrons in the what now? Conduction band will be increased more as compared to the what now? Number of the holes, I said now. Finally, majority carriers in n-type extrinsic semiconductor are electrons, I said only now. Understand the information regarding the n-type extrinsic semiconductor. A part of analysis also very important. Certain formulas also very important. Sorry, certain formulas I want to give from this only now. What those formulas we can give? Suppose the concentration of electrons in the conduction band, if you want to find concentration of electrons in conduction band, if you want to find, you can use n suffix n. N suffix n indicates concentration of electrons only now in n-type extrinsic semiconductors. That is calculated by formula Nd plus donor concentration. We are adding some impurity to the what now? Intrinsic semiconductor. There is a donor concentration. Nd plus under root of Nd square plus 4Ni square by 2. The formula is applied. Nd plus under root of Nd square plus 4Ni square by 2. By using this formula, concentration of electrons in the conduction band can be calculated easily only, we can say now. But how to find out the minority carriers in n-type extrinsic semiconductor are holes, we know that now. The holes in the n-type extrinsic semiconductor is denoted by symbol P suffix n. That's why you can write now. Concentration of holes they are the minority carriers, we can say, where number of the holes we can determine by using P suffix n. Number of the holes in are P, where in n-type extrinsic semiconductor. The minority carriers are generally calculated by using the mass action law. By using the mass action law only, it is calculated. What is mass action law? At thermal equilibrium condition, that means when the temperature remains constant, the product of concentration of electrons and concentration of the holes is equal to square of intrinsic concentration. What it says? N into P equal to Ni square. The formula is applied in the mass action law only now. N into P equal to Ni square only now. This formula is applicable for what? Intrinsic or extrinsic semiconductor. For both materials, it is applicable, this mass action law. I am repeating once again, what is mass action law? Under thermal equilibrium condition, the product of the concentration of electrons and concentration of holes is equal to square of intrinsic concentration. That is nothing but N into P equal to Ni square, we can write it now. By this formula is applicable for intrinsic and also for the what now? Extrinsic semiconductors, I said now. But anyhow, we want concentration of the holes Pn. How I can find? By using this formula, Ni square by Nd. N is approximately equal to Nd. Nd means donor concentration they will use. By using the what now? This formula, they will determine concentration of holes, we can say. Once we are getting the concentration of electrons and concentration of the holes, we can determine conductivity in n-type extrinsic semiconductor also. How that will be determined? You watch it now. The conductivity in, these are all the basics, very important to learn well about the p-n junction diode. Understand now. Conductivity in n-type extrinsic semiconductor. The conductivity is denoted by symbol sigma n. sigma suffix n, we can write it now, sigma n I can write. But here also what the conductivity due to sigma we can put y now, better to use sigma. Conductivity in n-type material now. How we can find conductivity due to electrons? Conductivity equal to already I gave it n into q into mu. Mu means mu n, n equal to n into nn. In n-type extrinsic semiconductor, concentration of electrons nn, how to find? I gave it nd. Nd will give in the problems donor concentration. Ni is nothing but intrinsic concentration. By using those two values, you can determine the what now nn only now. The once you got the nn, you can determine the what now pn also. Ni will give, nd will give in the problems only now. So but the conductivity due to electrons plus conductivity due to holes also more important. Conductivity due to holes means p suffix n into q into mu p they will apply. By using this formula, conductivity can be calculated only. What units must be used for conductivity? We know very well, mho per centimeter or mho per meter you can use. Understand now? That way we can find out. But sometimes in the problems he will give one condition. In case, one condition I want to give now. If donor concentration is given, nd value is given in the problem. If nd value is given very, very large as compared to the what now intrinsic concentration, suppose. When you compare with the Ni intrinsic concentration, nd is given very large. If it is given very large, you can say directly, then this nn is approximately equal to what? Nd only possible. These two are approximately equal. Nn and Nd are approximately equal when Nd is far more greater than Ni only now. If Nd is a very large means Pn, number of the holes are very, very less. Even you neglect it, it doesn't matter now. If you are neglecting the what now, concentration of the holes in the n-type extrinsic semiconductor, then I can write conductivity equal to, finally I can write the Nd into Nn equal to Nd I said. Nn equal to Nd into Q into mu n I can write. This is the conductivity formula we can use. It is approximately equal, I can say. Approximately equal to this only now. Understand, madam? Try to understand this, what is given. The last question, what is sigma equal to Nn into Q into mu n plus Pn to Q into mu p. But the concentration of the what Nn is approximately equal to Nd I said. Nd is a very large. When Nd is a very large, Pn is a very small. When Pn is a very small, we are neglecting. Whenever we neglected, in the place of Nn, directly I am putting Nd. And finally I got what I got finally? Sorry. Just a minute. Then Nn is approximately equal to Nd. Then we got as a, what we got? Okay, 1 minute. Okay, I'll put now directly. Okay. But we are getting finally what I said now, sigma equal to what we are getting? Nd, I'll write again. Nd into Q into mu n I gave already, approximately equal to, I gave already. Understand? That formula we are going to use. This is the information is more important regarding n-type extrinsic semiconductor, we can say. But I would like to do one problem based upon this formula. You can understand clearly well about this. A pure question I am giving here now. A pure germanium sample is doped with 4.5 into 10 power 16 per cm cube. Per cm cube is given. Per cm cube. Per cm cube is given. If Ni is given, intrinsic concentration is given. If Ni equal to 2.5 into 10 power 13 per cm cube. Per cm cube. Mu n equal to mobility of electrons. Mu n equal to 4,000 cm square per volt second. Cm square per volt second is given. Mu p also given. Mobility of holes also given in the problem. Mu p is given 2000 cm square per volt second it is given. That much it is given. And what is asking the problem? Is asking to find the first one, carrier concentration. Find carrier concentration. Carrier concentration. And second one here required is, first one is a carrier concentration I want, and second one is asking to find conductivity. Is asking to find the conductivity. Conductivity is asking to find conductivity. And third one is, I am giving the more questions here now at a time. And third one is nothing but the current density in the sample. 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 If electric field of electric field of 10 volts per cm, 10 volts per cm is given, is applied. Yes, this is one of the problem. How we can do this problem? That's more important. How we can do this question? In a problem, what is given? You watch. A pure germanium sample is doped with 4.5 10 power 16 cm cube. Doped with what? Doped with phosphorus atom. Doped with phosphorus atom. That's very important. Phosphorus atom. Phosphorus atom. Phosphorus atoms only here doped only now. Understand now? That is given as a 4.5 into 10 power 16 per cm cube only now. Otherwise, it is not specified that phosphorus are what you think it's so. We cannot understand is it a n-type or p-type only now. Anyhow, it is a pure germanium, means it is an intrinsic semiconductor. It is doped with a phosphorus 100%. It is a pentavalent atom only now. The donor atoms are, what the donor concentration Nd is given 4.5 into 10 power 16. I will write here now. Nd given, donor concentration is given. What is donor concentration here? 4.5 into 10 power 16. 4.5 into 10 power 16 per cm cube, which is given. Per cm cube it is given. And what about the next one? Next value it is given here now. You check it. And Ni is given 2.5. Yes, we can write intrinsic concentration is given. How much it is given? Ni equal to 2.5 into 10 power 13. 2.5 into 10 power 13 per cm cube we can write. And also in the problem it is given mu n and mu p also, I hope. Mu n equal to 2000. Mu n equal to 2000. 2000 cm square per volt second. Per volt second it is given. And also it is given mobility of holes also given in the problem. Mobility of holes equal to what is given? Mu p, sorry, mu n is a 4000. This is a 4000, this is a mu p we can put now. Mu p equal to 2000, mu n is given here. What mu n is given? Please watch. And mu n is given here. There is a mu p. And mu n is given here 4000. 4000 cm square per volt second it is given. And also in a problem it is given electric field intensity also. Electric field intensity equal to 10 volts per cm. 10 volts electric field E. 10 volts per cm I can write now. But in the problem what is asking, first question is nothing but the concentration is required. Concentration means concentration of electrons and also concentration of the holes. Both are required only now. So first we need to calculate both the values we can say. Both values are required. Understand now. Yes, good evening, good evening. Kishantu. It's a good evening. Yes, I would like to find the initially, what now in the problem is asking to find initially carrier concentration. The carrier concentration is nothing but, the first question is nothing but the carrier concentration is asking. Carrier concentration. Carrier concentration is nothing but, what I said, I want number of electrons and concentration of the holes also I want in the n-type external semiconductor. Those two are required. Without knowing those two, we can't get it only now. Understand now how we can get these two. The concentration of electrons already I gave it already. What is given already? Nn equal to what I gave already? Nn equal to. But a Ni value and what now? Ni value and Nd value you try to compare. Ni and Nd if you made the comparison is a 2.5 into 10 power 13 per cm cube only now. But here the Nd value is nothing but the 4.5 into 10 power 16. 10 power 16 is a very large number as compared to the 10 power 13. That's why we can write here now. What I can write here now? Nd is far more greater than what value? Ni value we got. Whenever Nd is a far more greater than Ni, directly I gave it already. Nn is approximately equal to what I gave it? Nd only. Let's say we are getting directly a Nn value. We no need to apply a formula, Nd plus under root of, already I gave it one formula. That formula is not applicable. Directly Nn is approximately equal to Nd. Nd is nothing but what is given 4.5 into 10 power 16. Same you can write per cm cube, you can write directly. Yes, we are getting Nn value. Now, by using the mass action law, we can determine the what now? The concentration of the holes only now. So, majority carriers, Nn is approximately equal to Nd, and concentration of the holes can be calculated by what I said, Ni square by Nd only now. Nd equal to Nn also we can write. Nd equal to Nn also, it is acceptable. I can write Ni square. Ni is nothing but 2.5 into 10 power 13 whole square divided by Nd is nothing but 4.5 into 10 power 16. Whenever you are using the calculator, its value will come as 1.38 approximately. You check it. If there is any mistake, you try to cross check this. 1.38 into 10 power 10 per cm cube is mostly possible. So, like that, concentration of electrons and concentration of the holes can be, because in the problem it is not specified. Is it required concentration of electrons or concentration of the holes? Directly it is given. Find concentration only. That concentration may be electrons or maybe holes also possible. That's why we can take both. Both we have to calculate only now. And what about the next question is asking in the problem? is asking the conductivity also. The conductivity equal to already give. When ND is a far more greater than NI, you think it's so. When ND is a far more greater than ND, the conductivity equal to what I gave already. Conductivity equal to ND into Q into mu N, I said already. This is approximately equal to this value only. The concentration of the holes are very small. We are neglecting. Electrons are more in the n-type extrinsic semiconductor. That's why we can take ND into Q into mu N only now. At the time, its value will be ND value. We know how much it is given. 4.5 into 10 power 16 we got. Into the Q is nothing but, you know very well, charge is nothing but 1.6 into 10 power minus 19. It is a fixed value. We must write as it is. And a mu N also given in the problem. 4000 is given here now. Whenever you are using calculator, its value will come as 28.8. But you calculate. If it comes same answer, okay. Otherwise, you change it. But the process is same only now. 2.8 into 8 mho per centimeter we can write. That way we can find conductivity value now. But the two parameters we got it now. And one more parameter is asking in the problem. Which parameter is asking to find in the problem? You check it. I got the what now? Current density. Sorry, conductivity I got. Current density also is asking. Sorry, current density is also asking. Current density is denoted by symbol J. I know, we know very well in the what now? Conductors I explain current density. I will explain here now. Current density is calculated by what formula? The current density we can calculate by using this formula. Current density. Current density is denoted by symbol J. I explained already in the conductors, current density equal to sigma conductivity into electric field intensity. Conductivity into electric field intensity equal to current density. I derived in the last class also now. So I will write directly this value. The sigma value we got just now. What value we got? 28.8. 28.8 into electric field intensity required 28.8 into electric field intensity equal to how much it is given in the problem? Electric field intensity is given as a 10 into 10. When you are multiplying with the 10, 288 it comes. But what are the units you will get here now? Units are nothing but amperes per cm square I can get here. Amperes per cm square I can get. Like that, the calculation of the concentration and also what? We got the second one, the conductivity, and third one, current density we can find. And one more question I will give now, because these are the informations is more important for PN junction diode, understand? But the heading I gave the PN junction diode, initially I wish to explain what is P type, what is N type, then after I will enter into the PN junction diode, understand now. The next question I will give now. But I want to give one more question now. The next question here given is a pure germanium sample. A pure germanium sample. A pure germanium sample. A pure germanium sample is doped with 10 power 14 arsenic atoms per cm cube. Per cm cube it is given. Per cm cube. If Ni equal to if intrinsic concentration Ni equal to 2.5 into 10 power 13, 10 power 13 per cm cube is given. That is the intrinsic concentration given in the problem. And also given in the problem, mu n is given, mobility of electrons here given, mu n equal to 3800 cm square per volt second it is given. And mu p is given here now, mobility of holes also given. Its value 1800 cm square. 1800 cm square per volt second we can take it now. The volt second possible. So this is the data is given here now. But what is asking in the problem? Is asking to find, then find carrier concentration. Carrier concentration I want. Carrier concentration and conductivity. And conductivity also required. And conductivity. Conductivity. This is the question was given. What way we can tackle this question? What is given in the problem, you check it. Then after you can try. But any student can give answer for this. Any student can do this. Any chances to get answer for this question? Anybody? Okay, I will do, please watch. But the carrier concentration is required means, you know, concentration of electrons and concentration of the holes also required. Both we have to calculate. We should not satisfy with any one of that concentration. Both are required, you know. And conductivity also asking here now. But how the formula is applied, here you watch. A pure germanium sample is doped with germanium. Pure germanium means intrinsic semiconductor is given. It is doped with 10 power 4 arsenic atoms per cm cube. 10 power 4 arsenic atoms. Arsenic equal to what is arsenic? Already I gave it. That becomes 10 power 14 only. 10 power 4 is a very small. 10 power 14, sorry. 10 power 14 arsenic atoms only. 10 power 14 means what happened now? This is a pentavalent atom only, we can say. Why it is a pentavalent? Pentavalent examples I gave it. Phosphorus and arsenic and also antimony. All these materials are given to you already. All are given here now. And intrinsic concentration 2.5 into 10 power 13 per cm cube is given. Mu n is given, mu p is given here now. But here the Ni is a 2.5 into 10 power 13 and Nd is given as a 10 power 14. 13 and 14 is very close only now. If Nd is a far more greater than Ni, then only you can take Nn is approximately equal to Nd only now. But in this case, I cannot take approximately those two are equal. Nn and Nd cannot be taken approximately equal here now. Why it is reasons are? The reason is what here? But in this problem, what is given here now? 10 power. It is given. First, I will give the data. You can understand here clearly now. I will take the solution. How I can take? Please watch. Here directly, I cannot take Nn equal to Nd. Why we cannot take? If it is a very large as compared to Ni, then only I can take. It is a 10 power 14, then 10 power 13 is a very close only now. In this case, Nn can be calculated by the formula which is given to you. Today I gave the formula. What is the formula given for Nn? Nd plus under root of Nd square plus 4Ni square, 4Ni square by 2. This formula is given already. This formula is given to you already. By using this formula, we can calculate. Anybody can give answer for this by using this formula? By using this formula, anybody can give or not? But a student should not say, sir, Nn is approximately equal to Nd, I will take, sir. No. When applicable, I said now, if Nd is far more greater than Ni value, but these two are approximately equal, we are finding 10 power 13, 10 power 14 only now. At the time, we can take Nn equal to this formula only. So what is ND here? Here ND is 10 power 14 plus ND square 10 power 14 whole square. 10 power 14 whole square plus 4 Ni square. 4 Ni square is required. 4 into, what about Ni? Ni is nothing but 2.5 into 10 power 13. 2.5 into 10 power 13. 2.5 into 10 power 13 whole square. 4 Ni square. 4 Ni square we can put now. 4 Ni square whole divided by 2. By 2. Use calculator, you will find what is Nn. That Nn value will be, that Nn value will come as 1.05, 1.059 into 10 power 14 per cm square, per cm cube mostly, per cm cube is possible. Nn value will come like this one, Such a way Nn is calculated now. But I want Pn also. Without Pn, I can't do one, How we can do Pn? Pn can be calculated by, the Pn can be calculated by, if it is a far more large, you think, so if Nd is a far more greater than what I said now, far more greater than Ni, Pn can be calculated by Ni square by Nd, I said here now. If it is not a far more greater than Nd, you think it's so. Nd is not far more greater than Ni, you think it's so. In that case, you must apply Pn can be calculated by Ni square by Nn only allowed. Don't put Nd here. Nd when allowed here now. If Nd is far more greater than Ni, then you can use Ni square by Nd. Otherwise, Ni square by Nn only it is allowed. Understand now. But what is Ni square? Ni square we know 2.5 into 10 power 13 whole square must be divided by how much? Nn. Nn is nothing but we got just now 1.059 into 10 power 14. If you are using the calculator, the Pn value comes as 5.9 into 10 power 12 per cm cube it is possible. Like that, concentration of holes can be calculated only now. Understand my point now? There is the concentration of the holes. And also in the problem is asking the what now? Conductivity. But a conductivity formula, what I gave it now, concentration of conductivity due to electrons plus conductivity due to holes, both are to be taken only now. But you should not take conductivity in the what now, n-type extrinsic semiconductor is not Nd into Q into mu n is not allowed. Why it is not allowed? If Nd is a far more greater than Ni, then only I can use conductivity equal to Nd into Q into mu n only now. But in this case, total conductivity equal to, how we can take? Total conductivity, you can take conductivity due to electrons, Nn into Q into mu n is a must. And also conductivity due to holes also required, Pn into Q into mu p1. No, it is required. Why we are using this formula? Here Nd is not far more greater than Ni value now. Then we can use this formula. So you can use, what is the Nn we got? We got Nn 1.059 into 10 power 0.5 into 10 power 14, I can write 10 power 14 into Q is nothing but 1.6 into 10 power minus 19 into mobility of electrons, mu n equal to how much? Mu n is given in the problem 3800. 3800 I can write. Plus the mobility, what now? Holes concentration, Pn also we are getting already. What is the Pn we are getting? 5.9 into 5.9, I am writing here now, 5.9 into 10 power, 5.9 into 10 power 12, 10 power 12 into Q is nothing but 1.6 into 10 power minus 19 into mobility of holes are required. Mobility of holes here given as what? Mobility of the holes are given mu p 1800 here given. 1800 I can take now. Yes, use calculator, you are going to get the conductivity. That conductivity value comes as sigma equal to, we can write 0.066 watt mho per centimeter possible. Mho per centimeter is possible. Like that, conductivity is also calculated one now. So, to know well about the PN junction diode, initially we got the information regarding the n-type extrinsic semiconductor. And also we need to know what is p-type extrinsic semiconductor and mathematical formulas regarding the p-type. Then after we can start the PN junction diode only now. Yes, we can start the p-type extrinsic semiconductor at first. I would like to do p-type extrinsic semiconductor now. I wish to do p-type extrinsic semiconductor. Yes, now we can do p-type extrinsic semiconductor. P-type extrinsic semiconductor. Extrinsic semiconductor. I would like to give information regarding the p-type extrinsic semiconductor. But after completing this p-type extrinsic semiconductor, I can do PN junction diode. I said already now. How the information is given based upon this p-type extrinsic semiconductor, you please watch. But how the p-type extrinsic semiconductor is formed, you take intrinsic semiconductor. Intrinsic semiconductor that is doped with trivalent atom. That is doped with trivalent atom. Sir, you are explaining the what no theory, that theory will be useful. Yes, in the gate theoretical questions only asking more in the what from the EDC. And also you can find the problems also. We should not neglect theoretical questions also in PSUs also now. You can expect questions from the what no theory also. So the foundation course you are going to learn well about the what no this theory. One theory and formula whenever if you know, you can do any question. You can go in depth also now, understand. But a trivalent atom means what? An atom which contains 3 valence electrons is called as a what no? Trivalent atom. As an example, we can take boron. Even aluminum also comes under trivalent atoms only, understand. Anyhow, as an example, I can use boron. One example I have taken, boron. You can take. I can write here now, trivalent atom means atom which contains 3 valence electrons. Trivalent atom means what? Atom which contains 3 valence electrons. Atom which contains 3 valence electrons. 3 valence electrons is called p-type extrinsic semiconductor. Sorry, is called trivalent atom. Sorry, is called trivalent atom. Trivalent atom we can call. Example I gave it boron. Otherwise, even you have taken aluminum acceptable. Followed now, pure semiconductor and boron, if you add it, it becomes p-type extrinsic semiconductor. How that structure is to be drawn? By watching the structure, you can get idea. What are the majority carriers are possible in this material one, Suppose I have taken boron. Boron is nothing but the B. You can put directly. But the boron, whenever it is a doped with intrinsic semiconductor like germanium or silicon, you think it's so. It can form covalent bonds due to sharing of electrons around the silicon atoms or germanium atoms. How means, please watch. I have taken pure silicon this side, germanium or silicon. The structure will be like this. This is silicon. It is also silicon here. This is one more silicon here. I selected one more silicon. Structure still goes this side and this side and this side and this side. It goes. The silicon contains 4 valence electrons, we know very well. I can put 4 valence electrons this side. It is a two-dimensional pattern is given. The 4 valence electrons here possible. And boron contains 3 valence electrons here now. It contains 3 valence electrons only now. 3 valence electrons. But because of the sharing of these electrons, thereby forming one covalent bond. Here forming one covalent bond at first. Here forming covalent bond. Covalent bond. Like that, how many number of the covalent bonds are formed in p-type extrinsic semiconductor? 3 covalent bonds are formed. But this electron doesn't have any more electron to form the bond. At the time, thereby created one hole here. Thereby created one hole only now. One hole is created, one vacancy is created due to lack of electrons to form the bond. Such a way, what no structure is formed. That means, so whenever you are adding one boron atom with what intrinsic semiconductors, then thereby forming one hole only now. Like that, number of boron atoms you are adding means number of holes are going to generate only now. Those are the holes will be occupying the space in between the what now? Fermi level only possibly. In between valence and conduction band only that is going to occupy. That means this is going to what now? Occupy the energy state just above the valence band only now. The name given for these holes is nothing but the acceptors. It is going to accept one electrons to recombine with it only now. That's why I can write energy band diagram. I can draw for n-type extrinsic semiconductor in this way. How we can draw this? How we can do? Please watch. Energy band diagram I can draw in this way. I can draw in this way. In the energy band diagram, you know very well, this energy is nothing but the conduction band energy, EC. This energy can be taken as what now? EV value only now. But where we can find the holes concentration to occupy energy states, what now? Energy states of these holes, excess holes will be here only possible. Here only they will occupy. This energy will be taken as a E suffix A, acceptors energy level only, that one. Understand my point? These are all with holes only now. You know very well, how can you say the majority carriers in p-type extrinsic semiconductor are holes? That is very important point only now. On what basis we say means, in the valence band, initially what now? Electrons are existing within the bond only. Within the bond, electrons are going to exist. When we apply temperature, bonds will be broken, electrons will be what now? Liberated. They will try to go from valence band to conduction band. And suppose the temperature here is very less, low temperature you got now. That means the electrons which are the low temperature means what happen now? First initially electrons will try to go and occupy this hole. The electron will go and occupy this hole. Hole is created. This electron will go and occupy this hole. Because this energy required is very less. Easily they can occupy these holes. The hole will be created, electrons will go and occupy here. Like that, what now? Certain number of the holes are created. Certain number of electrons from the valence band will try to go to the what now? This energy level in the forbidden energy gap. And they are going to occupy these holes only now. When the electrons are occupying these holes, thereby created holes only now. But we don't find any number of the holes where in the conduction band only now. Whenever still more amount of the what now energy if you applied, the electrons which are existing here will go to top and occupy this stage, may occupy this space, may try to go and occupy. Now, finally, what I wish to say, number of electrons in the conduction band are more, the number of electrons, number of holes existing in the valence band are more. 100% you can say hole concentration we can find in the valence band more only possible. The reason is what? Due to existence of the what now acceptors concentration, certain number of electrons are moving to the what now this energy level and occupying the holes, thereby creating the holes only now. And finally, majority carriers in p-type extrinsic semiconductor are holes only we can find only now. But how you can determine the hole concentration, that is more important. That hole concentration is calculated by the formula I will give here now. But the hole concentration, holes concentration in p-type extrinsic semiconductor, p-type extrinsic semiconductor calculated by number of holes in the p-type extrinsic semiconductor is calculated by Na. Na means acceptors concentration plus under root of Na square plus 4Ni square. 4Ni square by 2. This formula is applicable. Na is nothing but acceptors concentration will be given in the problem only. Ni is nothing but intrinsic concentration, then concentration of the holes can be calculated by this formula only now. But if you want to measure, if Na is, the point one more is recorded, if Na is just like a n-type extrinsic semiconductor, if concentration of acceptors is very, very large, suppose it is very, very large as compared to Ni, you think it's so. Na is far more greater than Ni, suppose you got. In that case, conductivity can be calculated by directly, I gave already formula. If Na is far more greater than Ni and concentration of the holes are approximately equal to Na, we can write directly. If it is greater than Ni square, Pp is approximately equal to Na only now. The conductivity is calculated by Na into Q into mu P will be used. By using this formula, you can use. Catch my point. If Na is a very, very large as compared to Ni square, Ni only, sorry. If Na is a far more greater than Ni, you think it's so. The concentration, the holes are approximately equal to Na only now. If these two are equal, conductivity can be taken Na plus Q into mu P. If this condition is not met, at the time conductivity equal to already given formula. Number of holes in p-type extrinsic semiconductor, the Q into mu P plus Np into addition is to be made, Nn into now. Anyhow, if it is a greater, that formula is applicable. If this condition is not satisfied, means you know very well. If this condition is not satisfied, means what I can say, the conductivity equal to what I said already, number of Pp into Q into mu P is allowed. Pp into Q into mu P plus N into P into Q into mu P is allowed. But the concentration of the holes can be calculated by concentration of the electrons in the p-type semiconductor can be calculated by mass action law only. I explained in the n-type. The same way we can calculate concentration. We don't need to go still depth only. That point is very important. Understand now. But this way we can tackle only, you can say. I hope so far you followed what is p-type extrinsic semiconductor, what is n-type extrinsic semiconductor. I explained only now. By using these two materials, how these two p-type and n-type will be useful in explaining the what a p-n junction diode, we will discuss in the next class. Thank you.